Hello and welcome to the Element Explorer. In this video, we'll dive into the fascinating world of elementary particles. These are the tiniest building blocks of the universe, and everything around us is made from them. Unlike most objects, elementary particles weren't made from something else. They came into existence from the energy released during the Big Bang. After the Big Bang, the universe was incredibly hot and dense. In the first few seconds, the first elementary particles formed: quarks, the building blocks of matter; leptons, like electrons and neutrinos; photons, particles of light; gluons, particles that hold quarks together. As the universe began to cool, these particles combined to form atoms. Over time, these atoms gathered to create stars, planets, and galaxies. From this early chaos, the universe started to take shape, leading to everything we see today. Imagine these particles as the alphabets of the universe. Just like every word is formed by combining the letters A to Z, everything in the universe is created by combining these tiny elementary particles. How many types of elementary particles are there? According to the Standard Model of Particle Physics, there are 17 recognized elementary particles. Elementary particles are divided into two main groups: fermions, which are the matter particles, and bosons, which are the force carriers. Think of fermions as the actual ingredients of matter, like flour, sugar, and eggs in a cake. Bosons, on the other hand, are like the invisible forces that hold everything together, like the heat in the oven that bakes the cake. Now, let's explore each category in detail. Let's start with fermions. These particles are what form all the matter we see around us. Fermions are divided into two types: quarks and leptons. Each type has 6 particles, making a total of 12 matter particles. Let's talk about them one by one. You might be wondering, can we see quarks? The short answer is no. Quarks are incredibly small, way too small for our eyes or even most microscopes. In fact, to see one, you'd need a microscope as big as the entire universe. But here's the interesting part: even though we can't see them, scientists know they're there. Let's rewind to the 1960s, where a physicist named Murray Gell-Mann had a big idea. He was studying particles called hadrons, things like protons and neutrons that make up atoms. He noticed something interesting: these particles weren't random. They followed patterns, just like how letters in a word always follow a certain order. Gell-Mann thought, maybe there's something smaller inside these particles. So, he came up with the idea that these tiny parts could be quarks. Testing the idea, now, scientists needed to find out if Gell-Mann's idea was true. To do that, they had to look inside protons. So, in the 1970s, they used a giant machine called a particle accelerator. They fired high-energy electrons at protons, expecting the electrons to just bounce off normally. But, plot twist. The electrons scattered in a weird pattern. This wasn't what they expected, which made scientists think, aha! There must be something smaller inside the proton. Fast forward to the 1980s. Scientists decided to try again, using a method called deep inelastic scattering. This time, they fired even more powerful electrons at protons and carefully watched how the protons broke apart. Guess what they saw? The protons broke into smaller parts, just like Gell-Mann had predicted. These tiny parts were quarks. It was like they solved a mystery, piecing together clues to discover something hidden inside protons. Think of it like a detective investigating a crime scene. Even though you can't see the culprit directly, you can follow the footprints they leave behind. That's exactly what scientists did. By following the strange pattern the electrons left, they figured out that quarks were real, even though they're too tiny to see. Now, here's a cool twist. There was another scientist, George Zweig, who worked on similar ideas at the same time as Murray Gell-Mann. In 1964, both Gell-Mann and Zweig independently suggested that protons and neutrons weren't indivisible, but made of smaller particles. Gell-Mann called these quarks, and Zweig called them aces. They never worked together directly, but their ideas matched up. Gell-Mann's quarks caught on because of a catchy reference to a book coming from a line in James Joyce's Finnegan's Wake, while Zweig's aces never really took off. Still, both of their discoveries helped shape the theory of quarks, and though they worked separately, their ideas came together to change our understanding of matter. Okay, so we've talked about quarks, but have you ever wondered how scientists figured out how to classify them? Well, first, they took a close look at the properties of quarks, kind of like getting to know a group of people and figuring out what makes each one unique. These properties include things like their mass, electric charge, spin, flavor, and color charge. Mass. Scientists grouped quarks based on how heavy they are. Imagine organizing a fruit basket. You'd probably separate the lightweights, like cherries, from the heavyweights, like watermelons. There are 3 types, or generations, of quarks, and they get heavier as you go from one generation to the next. First generation, the light ones, the up and down quarks are the lightest. These are the quarks that make up protons and neutrons, the building blocks of atoms. They're the most common and stable. Second generation, the heavier ones next, we have the charm and strange quarks. These are heavier and not found in everyday matter. They show up in high-energy places like particle collisions. Third generation, the heaviest ones finally, the top and bottom quarks are the heaviest. The top quark is the heaviest particle we've ever found. These quarks are very unstable and decay quickly. Here is a list of the approximate masses of each quark. Note that these values are approximate because quark masses are not directly measurable and are estimated from particle physics. Quarks can't be weighed directly like regular objects. Instead, scientists figure out their mass through high-energy particle collisions and math models. Here's how it works: high-energy collisions. In particle accelerators, particles are smashed together at high speeds, creating new particles. Scientists study the energy from these collisions to estimate the mass of the quarks inside them. Theoretical models. Scientists use special math to understand how quarks interact. These models help predict the mass of quarks based on what happens in experiments. In short, scientists can't weigh quarks directly, so they use energy from collisions and complex calculations to estimate their mass. Imagine a trampoline where people of different weights are jumping. Lightest people are like up and down quarks. These quarks need more energy to jump, but don't stay in motion for long because of their lower mass. They require more energy to start moving, and once they do, they quickly lose that energy and stop. Medium weight people are like strange and charm quarks. These quarks need less energy to jump because they have a medium mass. They require less energy to start moving compared to the lightest quarks and stay in motion for a bit longer because their higher mass helps them maintain that movement. Heaviest people are like top and bottom quarks. These quarks need the least energy to jump and move. Their higher mass means they don't need much energy to get started, and once in motion, they stay moving for the longest time compared to the lighter quarks. In short, the heavier the quark, the less energy it needs to move and the longer it stays in motion. Next, electric charge. Scientists looked at electric charge, whether a quark has a positive, negative, or neutral charge. Scientists already knew that protons have a charge of +1 and neutrons have no charge, 0. However, they didn't know that protons and neutrons are made up of smaller particles called quarks. Once quarks were discovered, scientists needed to figure out how these quarks combine to give protons and neutrons their charges. To determine the charges of quarks, scientists conducted high-energy particle collisions in particle accelerators. Through these experiments, they confirmed that quarks carry fractional electric charges of +2/3 or -1/3, depending on the type of quark. Here is the list of quarks and their charges. Alright, let's dive into one of the most fascinating properties of quarks, called spin. Quarks don't spin like tops or planets orbiting a star. Spin is a particle's built-in internal twist. It's not something you can see, hold, or even imagine in a physical sense. It is a fundamental quantum property that describes a particle's angular momentum. Let's compare spin to dance styles. Imagine quarks as dancers on a cosmic stage. Some quarks have spin up, like elegant ballroom dancers gliding across the floor. Others have spin down, like break dancers spinning with wild energy. Now, how did scientists figure out this concept? For that, we need to time travel back to 1922 and meet two brilliant physicists, Otto Stern and Walther Gerlach. In their famous Stern-Gerlach experiment, scientists shot silver atoms through a magnetic field. Instead of making one line, the atoms split into two lines. This happened because the atom's electrons have a property called spin, which can be either spin up or spin down. The experiment showed that particles like electrons can have different spin states. Imagine throwing a handful of coins through a giant magnet. Instead of landing randomly, the coins neatly split into two groups, heads and tails. That's essentially what the Stern-Gerlach experiment revealed about particles. Did you got any doubt? As protons and neutrons are made of quarks, but these quarks don't separate like electrons do in the Stern-Gerlach experiment. This is because protons and neutrons are held tightly together by the strong nuclear force, which is why they remain stable and don't break apart unless there's a lot of energy, such as in high-energy collisions or in dense environments like neutron stars. The strong force keeps them intact under normal conditions. Electrons are simpler particles, and their spin is easier to observe, which is why they behave differently in experiments like Stern-Gerlach. We'll explore electrons and these forces more later to help you understand them better. Let's come back to the topic. For quarks, the spin is 1/2, meaning they belong to a family of particles called fermions. Means, particles that obey the Pauli exclusion principle. The Pauli exclusion principle is a rule that says no two particles like quarks or electrons, which are called fermions, can be in the exact same energy levels at the same time. Imagine a classroom, and the seats are like different energy levels or positions. If two people try to sit in the same seat at the same time, they can't. Similarly, quarks or electrons in an atom can't all sit in the same energy level or state at the same time. All quarks have a spin of 1/2. Here's a list of the 6 types of quarks and their possible spin states. So, for each quark, you have the 2 possible spin states, spin up, +1/2, or spin down, -1/2. But a quark cannot have both spin up and spin down at the same time. Before we measure its spin, the quark can be in a state where it's kind of both at once, but once we measure it, it will be either spin up or spin down, never both together. This is known as quantum superposition. It's like flipping a coin. While it's spinning, it's in both heads and tails, but once it lands, it's definitely one or the other. Spin, along with the Pauli exclusion principle, plays a crucial role in the stability of matter. Like your chair or your phone, and whatever in this universe, don't collapse into a bunch of small particles because of the Pauli exclusion principle. They have to be in different ones. This is one reason why matter stays stable and doesn't collapse. Next, scientists refer to quarks as flavors to distinguish the different properties of quarks in particle physics. The term flavor is a metaphor used to describe these different types of quarks. There are 6 recognized quark flavors. The naming of quarks was not based on any physical property, but was instead influenced by their behavior. First, we have the up and down quarks. Now, these are the most basic ones. The names were picked just for convenience. They were easy to remember, and they helped physicist Murray Gell-Mann explain how protons and neutrons are built. Next is the strange quark, and this one got its name because of some weird behavior scientists noticed. Back in the 1950s, certain particles containing strange quarks didn't decay as quickly as expected, so they called them strange because they were acting, well, strange. Then there's the charm quark. This one was discovered in the 1970s, and when scientists found it, they were so excited, they decided to call it charm. It was a discovery that really charmed the scientific community. Now, the top and bottom quarks. These names were chosen later on, in the 1970s, and they're pretty simple, just like their names suggest, they're at the top and bottom of the quark hierarchy. No fancy reason behind it, just a neat way to keep things organized. So, even though these quark names sound a bit playful, each one tells us something unique about the properties of quarks, like their mass, charge, and how they interact with other particles. It's just a clever way for scientists to keep track of these building blocks of our universe. Quarks also have a property called color charge, but it's not about actual colors like we see. Instead, quarks come in 3 types of color charges: red, green, and blue. When quarks stick together to form things like protons or neutrons, they mix their color charges in a way that balances out to a neutral color. We'll go into more detail about this when we talk about gluons. Gluons also have color charge, so the color charges of gluons and quarks are closely related. Stay tuned for a deeper dive later. Let's explore the differences between quarks and antiquarks. Charge: quarks can have either positive or negative electric charges. Antiquarks, on the other hand, always carry the opposite charge. For example, if a quark has a positive charge, its corresponding antiquark will have a negative charge, and vice versa. Color charge: quarks also carry a property known as color charge, which is related to the strong force. Quarks can have one of 3 color charges: red, green, or blue. Antiquarks carry the opposite color charge: anti-red, anti-green, or anti-blue. Combination of quarks and antiquarks: quarks combine in groups of 3 to form baryons, like protons and neutrons. Antiquarks combine with quarks to form mesons, which are another type of hadron. We will explore the details of color charge further in upcoming discussions. Here's a table that summarizes the particles quarks can form, their composition, and their relative abundance. First, we have baryons, which are made up of 3 quarks. These quarks can be any 2 of the same type and 1 of a different type. The most common example is the proton, which consists of 2 up quarks and 1 down quark. Protons and neutrons, which are made of different combinations of up and down quarks, are naturally abundant and form the nucleus of atoms, making them essential to all matter around us. Then, we have lambda baryons, sigma baryons, and delta baryons. These particles are made up of a mix of up, down, and strange quarks. However, they aren't naturally abundant in our everyday world. These particles are typically created in high-energy environments like particle accelerators or cosmic ray interactions. Next are the mesons, which are made up of 1 quark and 1 antiquark. For instance, pions are the most common mesons, naturally produced in cosmic rays and high-energy interactions. But kaons, eta mesons, charm mesons, and bottom mesons aren't naturally found in everyday matter. They are generally formed in high-energy collisions in particle accelerators. Finally, we have exotic hadrons, like tetraquarks and pentaquarks. These are made up of 4 or 5 quarks, often including both quarks and antiquarks. These particles are extremely rare and are only observed in advanced particle physics experiments, not in natural conditions. So, while some particles, like protons and pions, are naturally abundant, others, like mesons and exotic hadrons, are formed in rare, high-energy processes that we mostly observe in labs. And that's how quarks combine to form all the matter and exotic particles in our universe. Till now, we've learned about elementary particles, including all 6 types of quarks and their properties in detail. In the next video, part 2, we're going to discuss leptons and bosons in even more detail. If you found this video helpful, please don't forget to like and subscribe to the Element Explorer for more exciting and educational videos. Stay tuned for more fascinating insights into the world of chemistry.